just to kick off, today I'm on the lands of the Kulin Nations here at Monash University, Clayton, and I also know that RMIT rests on the lands of the Wurundjeri people of the Kulin Nations. But wherever you are right now, we wish to respectfully recognise the traditional owners of these lands and their elders, both past, present and emerging. Thank you everyone for joining us today. My name is Philip Heath. I'm the Hub Manager of AM2D. I don't want to waste your time with things not relevant to the talk, so I'll just spend 30 seconds to say, please follow us on LinkedIn. There's a QR code there, or you can look us up at ARC_AM2D. Please follow us there for upcoming events, talks, and updates on the latest things that are happening around the Hub. I also want to mention that this event is co-organised by RMIT and Monash University. And finally, I just wanted to mention we have a two-day workshop coming up, 2D printed devices workshop. More details on this will be released very shortly, but I just wanted to mention that this event, this workshop is intended to connect and build the 2D printable devices community in Australia and internationally. And we have speakers from academia and industry, both nationally and internationally, lined up for that event, and we'll be releasing some more details about that shortly. I'd like to pass over to Somak. Namita, did you want to do an introduction to Somak, or do you want me to?
I'm happy for you to do that.
Okay, no worries. So Somak.
Or create other problems. So let's start quickly. Yeah, thank you.
No worries. So Somak, Professor Somak Chatterjee, he's from the Department of Chemical Engineering at the Birla Institute of Technology and Science. He is going to talk to us today about functionalized materials for water purification. Somak, I'm going to stop sharing my screen and pass over to you. Just give me one moment while I do that.
So thank you, Phil. And first of all, I'd like to thank Professor Namita Chaudhary and Professor Nabadatta over here at RMIT for inviting me. And my visit to RMIT has almost come to the end. So I'm leaving for India on 13th, and this is practically my last working day over here. So thank you very much, madam and sirs. I think Professor Datta is also has also joined, and thank you very much, sir, for hosting me over here and making my stay such pleasant at RMIT. And practically just before joining in this talk, I'd like to mention that this is my first time in Australia. I have been to various places like in Europe, in Australia, in US, but like coming into the picture, Australia, it had really taken a heart. It's really taken a place in my heart, and I'm really overwhelmed by the hospitality of the people over here, and such a good people that we have in the place that where I'm visiting. So it doesn't feel that I am away from my home, but it feels like a second home to me. So thank you very much, and also to Phil for organizing this AM2D event. Where Professor Chaudhary is one of the main coordinator, and she was so kind to allow me to speak over here. So that's all from my end for the introduction. So coming on to the other parts, I'd like to give a quick overview about me, what I'm doing currently in the research front. So practically, a brief history starts from my journey in 2007. I completed my bachelor's in chemical engineering from Heritage Institute of Technology in Calcutta. I started in 2007, completed in 11. And following that, I did my master's from IIT Kharagpur in the Department of Chemical Engineering, and I finished it off in 2013. And it was a continued version, so I immediately joined into the PhD program. And from the same department, and my faculty and the PhD supervisor or the MTech supervisor was the same, Professor Shishendu Dey from IIT Kharagpur. And I completed my PhD in 2018. Following that, I was recruited as a senior engineer in the refrigeration and water purification unit in the GEIDC of Tech Mahindra Technology Center, which is actually a branch of GE Appliances in Hyderabad. Following that, I worked as a senior scientist in Aquaworks, which is a R&D division under Marman Waters. That's, again, a subsidiary company of Berkshire Hathaway, and I was based in Bangalore. After a short stint over there, I joined as an assistant professor in the Department of Chemical Engineering in BITS Pilani, Birla Institute of Technology and Science Pilani, in the mother campus. That is the Pilani campus, and I am based in the beautiful place of Rajasthan. So I'm working as an assistant professor over there. So this is actually my current location where I'm based. This is the famous clock tower that we have, and this is the famous department from where I belong to, from where I represent where I started my journey as a affiliated independent researcher. So these are going to be the contents of my slide. I'm going to talk about functional materials. Firstly, what is functional materials and what are functionalized materials? And I'm going to take two examples that is based on beads and something known as a moth cloth. Since most of the time will be taken to explain the experiments or the detailed version or the detailed results that I obtained in these two cases. Followed by that, I'm going to talk about few important other works that I have presented. The prototypes that I have developed throughout my research career and the lab that we have, it's known as the Water and Energy Sensor Lab, and that's based in the Chemical Engineering Department at BITS Pilani, and the facilities that we have over there. So coming on to the factors, so what is a functional material? So as we all know, a functional material is consisting of various types, like you have carbon-based material, polymer, energy storage material, semiconductors, hard material. So anything, any sort of any sort of material which is having any functional properties that's designed to perform electrical, magnetic, optical responses, energy storage functions, or any other leveraging properties, those are actually meant as functional materials. And they can be used for a varieties of application, starting from nuclear field energy, biocompatibility, medical applications, optoelectronics, in energy sectors, in the aerospace, any sort of functional materials that works over here. And since this hub is actually working on materials, so functional materials plays an important part in the hub activities, where you can see there are 2D graphene materials or even 1D materials for CNTs, conductive polymers, conventional materials, MZenes, metal nanowires, all the stuffs which plays an important part in our daily-to-daily activities and also high-tech activities of our daily in our life. So the next part which comes into play, so what is the opposite of that? So that opposite of functional is the non-functional. Obviously, it comes by colloquial English dictionary. So a material which lacks any native property. All this material has good properties. So the last bencher of the class who doesn't know about the subject, who has failed in the subjects. So in all the subjects, these are non-functional materials. So our job as a faculty is to train those failed students and make them pass. So what we do is we call it as the functionalization. So we train those students, and functionalization is a part of training, and we make it as a functionalized materials. And in our case, this functionalized material is desired to have any functional property of our choice. And the desired property that we we selected in this case was based on water treatment. So one of the example of non-functional material like a polymer we took, we functionalized it and we made in the form of something known as beads. And the second one, we used again a non-functional material like a filter paper. We functionalized it and we made something known as the moth cloth or the moth filter paper. So I'm going to talk about these two examples in my talk over here. Now, coming on to water treatment, a brief overview of different pollutants that we have in our ecosystem. And they mainly can be divided into two groups. One which is present in abundance, that is a long, or they are present in a huge quantity, which is known as a macropollutant, and the other one is a micropollutant. They are present in small, but they create havoc, diseases or catastrophic diseases in the human in the human body or in other areas, and they are present in small amount, and mainly the contaminants which are into this classes, they belong to heavy metals, pathogens, and organic solvents. Now, our main or our main motive in order to take into water treatment over here is to concentrate on something known as the macro pollutant, and under macro pollutant we take into account something known as one of the menace. It's required in small amount in the human body for calcification of our bones, for our teeth, for hardening our teeth or bones, and required as an essential micronutrient. But when its concentration increases in huge amount, it starts causing detrimental effects, and that
मैं
material
तुम्हारा
of
वेट
that.
करूँ नाश्ते के लिए, आ जाओगी 10-15 मिनट में ना? चलो आ जाओ.
And sorry for the glitch, someone was talking. Anyways, so then that material which we actually concentrated over here, which is essential micronutrient, but when it increases its concentration inside the human body, it starts causing detrimental effect, and that is fluoride. So fluoride is present in our toothpaste. It is used for various applications, as I said, for dental calcification, for bones hardening, for making the regeneration of our neural fibers. But when its concentration increases, it creates havoc disease. So the causes of this fluoride leaching can mainly be divided into two parts. The first part is the leaching from fluorosilicates or fluoropartite drops. These are naturally present, and these is natural means of fluoride for increase in fluoride concentration in the groundwater. And the second part is by our application, that is the anthropogenic causes. For example, leaching from industrial wastes of aluminum, zinc, and copper producing industry. We have fertilizer industries and toothpaste producing companies. The health issues, when it starts increasing its concentration, instead of regenerating the fibers, it can start acting as a neurotoxic agent, mainly giving rise to diseases like Alzheimer's, Parkinson's, and the main effects are the effect which is seen in the body. It's dental and skeletal fluorosis. So where the teeth actually starts deforming and the bones, they permanently gets deformed. It also impairs the immune system. It tries to compete with the immune system, and thereby when the immune system gets degenerated or it gets deactivated, a lot of other toxic health effects starts showing up in the body. And apart from that, once the immune system is compromised, the repetitive stress injury takes place. So the average concentration which is seen in polluted water for fluoride ranges from 6 to 12 milligram per liter. But as per the World Health Organization's limit or classification, it should not be greater than 1.5 milligram per liter. So coming on to the presence of fluoride, we can see that it's scattered all over the world, and the probability that its presence in groundwater can be seen for greater than 1.5 milligram per liter. You can see various parts, like in parts of India, in the middle and the southern part of Australia. The probability or 80% to 60% probability is there, where the concentration of fluoride in groundwater can be seen greater than 1.5 milligram per liter. Apart from India and Australia, you have the presence in the United States, in eastern part of African in the eastern part of African continent, in the Middle East, as well as in Latin America. So when it comes to India, a varieties of states has a lot of fluoride concentration. And the part that I am actually based in, it's in Rajasthan, and you can see the 80 to 100% of the districts are getting affected with the menace of this endemic fluorosis. So when it comes to the speciation study of fluoride, usually in the range of drinking water for 7 it's either present as fluoride anion, and in the acidic pH, it's present in the form of HF2, that is hydrofluoronium ions, or hydrofluoric acid based ions, which are mainly being seen in the acidic range. But when it comes to the basic range or in the neutral pH, fluoride is mainly present as fluoride anion. So the first work, this two works that I will be talking about, has been published in the Journal of Environmental Chemical Engineering, where we had made composite polymeric beads and MOF cloth, and these are mainly used for defluoridation applications. So coming on to the first work, that is on beads. The beads are actually something made by phase inversion method. So what we do is we use a polymeric solution, a molten polymeric solution, where the polymers that I mentioned, for example, over here we are talking about polyether sulfone. It's been dissolved at high temperature in dimethyl formamide solvent. And once it is dissolved and homogenized properly, we use it in a syringe pump. And with the help of a syringe pump, we continuously push it in the form of droplets to the water stream. And once this falls inside the water stream by a mechanism known as phase inversion, it starts getting transformed into solid structures. Now, why phase inversion? Because the normal method of phase transformation is from solid to liquid to gas. Now, when you have a liquid polymer solution, it gets transformed into solid. You have something known as the phase inversion process, and this mainly occurs when the polymer starts coming from the binodal zone to the spine, from the binodal zone to something known as a single node. And that single node starts helps in the formation of this polymeric beads. And these beads that we get in, these are used for further characterization for making the best ones, and the best ones are used for defluoridation studies. So I'll show a quick video about how the beads are made, although I explained it, but I think a videographic structure might be fruitful for all those who are listening to this talks. So this is how this is made. As you can see, the syringe pump is continuously pressing the syringe piston, and the polymer solution is getting inside the water. The droplets are falling, and once the droplet falls, you can see over here. So just a minute, I'll make it in the form of a pointer here. So you can see over here, this is actually so getting up in the form of this bead structures. Okay. So it starts falling down, and it gets into this bead structure, and this is how the entire setup actually looks like. It's very cheap, and it's cost-effective method of producing such beads. This becomes in the form of like adsorbent materials. So the different type of beads that we prepared, the first one, we call it as the control, or the B1 beads. That's made up of something known as polyether sulfone, pure polymer. After that, we started preparing something known as we got some conductive polymers like polyaniline and polypyrrole. So polyaniline, we had some undoped structures in polyaniline, whereas if it starts some doping structures in polyaniline, these two are different polymers that have been used to make this blended polymer solution. And finally, we can also use polypyrrole. And we saw that the surface area, although it's comparatively very small, and the viscosity, it's comparatively very high. But when it comes to polypyrrole beads, the hydrophilicity of the beads, it's extremely high. And it can be seen with the reducing contact angle that these are forming spherical structures. Now, once we had the beads, it came to our mind to continue with the with the characterization. The first one is to see the morphology, and we can see structures like this rough and rugged structures on the surface. So first one is the control, that is a pure polymeric beads, followed by B2, which is consisting of polyaniline, that is the undoped one. Then we started adding polyaniline to PS, that is polyethersulfone, the doped one, and the final one is the polypyrrole. So these are these resembles or this mimics mainly crystal structures on the surface, very haphazard crystal structures. And the cross section somewhat looks like this, which is something looking like a flower once. And now we went into deeper correlation, and we saw that there are, when we look into the structures at a higher magnification, there are pores or strong, larger pores, which actually can help to imbibe the fluoride inside or the water inside, and the material which is inside, it starts interacting with it. So also we used FITC dye, fluorescent dye, in order to color the beads and see its spherical shape, and thereby we were certain that the spherical shape was necessary in order to impart absorbent structure to the material. Next, we came across this XRD, and what we were actually able to see is the sulfone groups, the pyrrole groups, the aniline groups. They are mainly being observed by various peaks that have been shown. The main one over here is at 47 degrees, which corresponds to the aniline group in the polypyrrole. And also in aniline group in polyaniline, and in pyrrole groups that is mainly represented in 29 degrees. We also carried out analysis with the FTIR, and various functional groups were observed in this case. Also with the TGA structures. So now the reason for doing the FTIR is to ascertain whether the functional groups that are mainly lying in this case is at a stretch between you can see it's from 3,300 till 1240, and also the lower peaks, it ascertains to the distribution of different other functional groups, like, as I said, aniline. You can have hydroxyl groups, the sulfone groups, the aniline structure, the dopant, that is the lauryl sulfate, that is present. And in this case of this, the TGA, that is the thermogravimetric analysis we did, so we can see that the major weight loss, it occurs at a temperature of around 600 degrees Celsius. So the degeneration mainly starts from something at 100 degrees Celsius, and it completely degenerates at a temperature which is starting from around 600 to 650 for all the beads. We carried out an XPS analysis in order to ascertain whether the hybrid orbital, it is able to take the fluoride ions that when we are actually putting it in a solution consisting of fluoride. So we can see that F1s, it represents the orbital shells of fluoride, and that is getting in the adsorbed B4 beads. Now, why we have to choose B4 bead? Because of this one, that is, it is giving a very high uptake capacity in comparison to what we call as the what we call as the equilibrium uptake capacity, which is the highest for the B4 beads. It's around, like you can see, it's 25 to 30, and it starts on increasing as we increase the temperature. The reason being fluoride ions, which is showing increasing mobility at higher temperature, and when it has higher temperature, this becomes a sort of endothermic reaction, and this is endothermic adsorption process. Now, coming on to the pH study. So we did a pH study as well, and we can see that as the pH starts on decreasing, the removal percentage also starts decreasing. And the reason behind the isoelectric point of the beads is at 3.4. So when the isoelectric point is lesser than the pH ZPC, that is the pH at the 0 point charge, the surface of the bead is actually positive. Whereas if it is greater than this isoelectric point, the surface of the bead is actually a negative. So in case of negative surface charges, mainly the surface of the bead starts repelling, and by repulsion, the removal of fluoride is not that effective. But when it comes to something as lesser than the isoelectric point, the surface of the bead being positive, it starts attracting and it gets imbibed within the hollow pore structures that are present inside the beads. Also, we carried out analysis with the effect of different coexisting ions like chlorine, carbonate, bicarbonate, magnesium, calcium, and potassium. The reason for choosing is these type of coexisting ions are present in abundance in normal groundwater. And we were able to see that the maximum coexisting effect is being shown by potassium. The reason being of the fact that potassium being a positive ion, so when mainly the surface of the bead is negative, again, it starts attracting the positive potassium ions. But in case of the other ions like magnesium or calcium, you can see that there is an effect, but not that much in comparison to the potassium because it contains it has dipositive charges and it starts attracting the potassium ions. We carried out analysis with that of the effect of dosage as well, and this was done mainly with two concentration of fluoride, that is at 10 milligram per liter and 100 milligram per liter. At 10 milligram per liter, we can see that if it is at 50 gram per liter of fluoride, 50 gram per liter of the dosage, it is it's actually getting saturated. So you can use something which is about 50 gram per liter, where this beads can completely remove fluoride. But compared to higher concentration, the saturation effect was not seen because the concentration of fluoride was in abundance, and thereby you could have you need to actually increase the concentration or increase the concentration of the dosage to something as 100 or even more than that, for 100 gram per liter or 150 gram per liter of the adsorbents. We carried out the kinetic and the regeneration studies as well. The kinetic studies showed that the saturation was obtained somewhat between 1000 minutes to, it was carried out till 2500 minutes, and we also included tap water as well. And in tap water, fluoride was there because we live in a place where fluoride concentration is higher than the WHO limit. And we carried out the analysis in order to see that it starts from 1000 till part where saturation starts taking place. Coming on to the regeneration study, so you can see that after the third and sixth cycle, some of the active sites are permanently lost, and when it's permanently lost, the uptake capacity, it is decreasing heavily, and they are not able to recover. But still, if you see after the sixth cycle, the uptake capacity for the bead, for the exhausted bead is still 18 milligram per gram, which is comparatively higher than some of the conventional adsorbents. Now, batch studies are something in order to carry out an analysis for the equilibrium uptake capacity. So you need to understand the dynamic capacity so that it can be used for scaling up applications. So we used a microcolumn like this, where we used a bed height of around 6.5 centimeter. And we used gravitational method because most of the cases we should actually see that if energy is not utilized, what can be the effect for actually carrying out the studies. Because if you use energy, if you use a pressure, you can use full bed or you can use a effect of full utilization of the bed. But in gravitational method, there is no energy utilization is taking place. But again, the full bed utilization is not taking place because of the shortest part taken by the water stream. We used a flow rate of 80 microliters per second, and we used again a syringe over here, which was available with us. And we carried out an extensive analysis to see at two cases. One was with the lab water simulated fluoride solution, and other one was with the tap water simulated fluoride solution. So we can see that with this one, the bed volume was actually 0.1, the number of bed volume. So if you carry out, or if you calculate the bed volume and multiply it with the number of bed volume, you can actually get how much amount of filtered water has been taken or is practically generated. We carried out COMSOL-based analysis, and we can see from the lower graph that the one which is having for the synthetic solution, it nearly matches. In case of tap water solution, also there is slight deviation because of the presence of different other coexisting ions, which causes hindrance to the effect of fluoride solution, but somewhat at the end, that is at the frag end of our experiment, it also starts mimicking the experimental studies that we have done. Now, coming on to the, after taking into account so much analysis, we carried out an extensive study about to understand what can be the major uptake mechanism. So over here, you can see that B, which is the lauryl sulfate ion that is present in the conductive polymers, they actually plays an important part in order to exchange fluoride. So the lauryl sulfate ion being present in the structure of polyaniline, it actually affects, or it actually in exchanges with the fluoride ions, and thereby the lauryl sulfate ion gets out and fluoride ions get stuck in onto the polymer, that is the composite polymer structures that are present. We also carried out an analysis about the uptake capacity and the material cost mainly. So the with doped polypyrrole in this DMF solvent, the uptake capacity was nearly 40 at 298 Kelvin, that is 25 degrees Celsius, and the material cost was around $8 per gram. In comparison to most of the polymer structures, like you have polyaniline, polypyrrole, they are having high material cost, but the uptake capacity is comparatively low. The only one that is near is titanium dioxide, which is modified with polypyrrole. Again, the uptake capacity, it's around 33, still lesser than the one that we has achieved, and the material cost also is comparatively high. Now, coming on to the next part, which is the MOF and MOF cloth. So coming on to the MOF that we used aluminum terephthalate MOF. So in this case of aluminum terephthalate MOF, the major solvents or the major reactants that were taken into account is we require a salt. We used aluminum nitrate monohydrate in this case. A solvent, which is again DMF, that's the most abundantly available solvent that we have in India. A reactor, or by means of which a reaction mechanism which can start is the amino terephthalic acid, and hydroxyl important group over here where we used methanol. Now, the reason for using methanol, I'll just explain in my next slide, or in this slide over here. And by means of hydrothermal reaction, we can get aluminum node, which sits in the BDC, that is a terephthalate ligand. So we get this kind of yellowish powder, which is aluminum terephthalate MOF structures. And why we used methanol? Because it's been toxic. What is the need to use that? Because there are different types of hydroxyl important groups, the major being hydroxy terephthalic acid. But hydroxyl terephthalic acid, it's being, again, a very costly group for importing the hydroxyl ions. So we instead used something for methanol. You can see over here, we carried out an analysis for the fluoride studies, for the fluoride uptake studies. And we were able to find that with methanol being taken into account, or methanol to amino terephthalic acid being taken into account in 1:1 ratio, the uptake capacity reaches at 665 milligram per gram, which is very high in comparison to some of the MOF-based solvents. But however, the yield of the MOF is something which is very low, and people are finding means to actually increase its yield. So instead of finding so much detailed network, we try to take the shortest route. And with the help of shortest route, what we try to do is we synthesize this MOF, and we utilize this MOF in order to immobilize on a surface, and that surface was a filter paper. So how we did it? We used something known as the carboxylation. So firstly, we used this filter paper and we used carboxylation method, where we imported these sites for anchorage sites where this MOF can be imported onto the filter paper. And once we imported the MOF structures, as you can see from the same images, this MOF gets deposited on the surface. And instead of calling it as the filter paper, we start calling it as the MOF cloth. So this entire thing we immobilized on the surface of the filter paper and we started calling it as the MOF cloth. And this can be used for, again, a sort of defluoridation application. So as you can see, the one which is we have the MOF that we made, and the size distribution was in the range of 0.1 micron. And this one was that of the filter paper that we had. And this is the carboxylated filter paper, the CMP that we call. So it's containing the anchorage sites. The anchorage sites gets tightened. And once the anchorage sites gets tightened, we can actually deposit the MOF onto the surface. Now, the reason for doing an XRD study over here is to ascertain whether in the MOF cloth, the one that we have in carboxylated filter paper or carboxylated methyl filter paper or the one that is present in the aluminum MOF, it's whether it's present in the main MOF cloth or not. And we were able to see that most of the peaks were we were able to see. In this case, 44.3 is mainly the reference peak in the MOF powder, and this is present in the MOF cloth as well with a slight deviation. In case of the TGA, that is the thermogravimetric analysis, we were able to see that the weight loss, it actually starts happening, or the complete weight loss starts happening at a range from 400 to 700 degrees Celsius. But in case of the carboxymethylated filter paper, the weight loss, it's actually much more faster. But when we deposit the MOF cloth, because of its high resistance to heat, the degradation starts at a much at a temperature which is comparatively higher. We carried out an analysis with the FTIR where we were able to see that the hydroxyl group, the alkene, and the carboxyl group were present. The alkene and the alkyne groups, and we were able to see that with the MOF cloth. And once we equilibrated the one with fluoride solution, the transmittance gets higher. Why? Because of the fluoride incorporation within the peak or within the structure of the MOF cloth. And again, similar to that of the beads, we were able to see that fluoride orbitals present in XPS analysis, along with the oxygen, carbon, and the aluminium one that is present in the structures. Again, we carried out different equilibrium studies. So I'll go back to the previous slides to show that in this case, it was around 665, but as the yield is very low, we have to immobilize it in a material to get something which can be used for daily application. So from 665, as it's getting immobilized and some MOF are getting lost, so the defluoridation capacity, it decreases to 80 milligram per gram, but still it's high. So we carried out an analysis for the equilibrium study, and also we were able to see that as the temperature keeps on rising, the uptake capacity of fluoride also increases, giving rise or suggesting that it's an endothermic absorption mechanism which is happening. Now, in case of the removal, we studied with pH, and we were able to see that again, as the ZPC is near to something like in the acidic range 4 or 3, when it's greater than 4, the surface being negative, it repels fluoride, whereas if it is lesser than 4, the surface being positive, it tries to attract fluoride. And the regeneration cycle also we were able to see, but in this case, the MOF cloth, the regeneration after second or third cycle, it completely diminishes. and the active sites are completely lost. We carried out analysis with the anions, and in case of anions, we have chosen carbonate, bicarbonate, and chloride, and along with it, we chose TMTDS, which is tetradimethyl sulfate, which is also named as thiram, and this is present in the pesticides actually. So we carried out an analysis with that, and we were able to find out that at increased concentration, the chloride ions, it can start hampering with the MOF and start competing with for the MOF anchorage sites for fluoride. We carried out an analysis for the aluminium as well, because aluminium being another harmful metal ion. So this is the EPA limit around 40 to 50 microgram per liter. And we were able to see that, yes, over a period of 24 hours, there is leaching of aluminium taking place, but leaching is much lesser in comparison to the EPA limit. Now, with this one, we carried out another dynamic study where we used a vacuum pump, and we used filtration apparatus, where this MOF filter paper can be attached, and continuous flow of fluoride-laden solution was taken into account. And the concentration of the feed was nearly 2, which is higher than 1.5. And over a span of time, where 400 ml of water for that short amount of filter paper, where the filtration area, you can see it's around 0.017 meters square. It's very small. We can get filtered water for that. Even we could have continued, but still we thought of stopping the experiments over there, because it's not increasing. So it's a safe filter paper, or the safe filter paper or fresh water which can be obtained from contaminated feed. The mechanism which we understood, it's mainly occurring by an anion exchange mechanism, where the aluminium node that is present in the BDC ligand of the MOF structure in the filter paper, the fluoride ion, it gets exchanged with the hydroxyl ion that is present. The hydroxyl group being the main prominent structure over here, and the fluoride ion gets attached to the aluminium node in the BDC ligand, whereas the hydroxyl group, it gets dissociated in the water solution. We carried out again a comparative analysis with different type of MOFs that is being used for fluoride removal, and we saw that in most of the cases, the ALBDC MOF, it has high capacity, around 665, and the material cost is roughly coming to be around $2.3 per 100 gram. Whereas if you are taking the MOF cloth, the highest capacity, it's coming to be around 88 milligram per gram, and the cost per meter square of this MOF cloth is around 15.5. Whereas in most of the cases, you can see that for MOF 801, the UIO MOF, which is again a mimic form of the BDC MOF, the aluminous zeolite, most of them has very low capacities compared to in the range between 40 to say 100. The highest one being the composite nanofibers by the amide-based MOF, which is around 95, but still it's much lower than the LBDC MOF. In the MOF cloth, when it's mobilized, because we cannot have a scaled up version of LBDC MOF, so therefore it cannot be used, and thereby it is something coming to be around 88, and it can be used for long-term study as well. So this was the two major examples that I had taken, or in order to explain the usage of the functionalized material in one of the most important application in our daily life, that is on water treatment. Apart from that, we had carried out extensive number of studies which has been published in various journals. This one was on electrospun nanofibers, again composite, or I should say a blended polymer, which is being used for coaxial electrospun nanofiber. This is also used for fluoride removal. The latest one which got published in RAC Advances was for the composite coaxial electrospun nanofibers. that is again used for fluoride removal. But again, we used a micropollutant over here, which is a harmful heavy metal, that is lead. We used the composite. We used the polymers, which is conductive polymers like polyaniline for defluoridation, and we used undoped and doped both to see how it can affect the for defluoridation and lead removal. So, in case of polyaniline doped based material, it shows as a promising adsorbent for fluoride removal, whereas when we use undoped polyaniline, it can be used for lead removal because of the charges that is being imparted in the conductive polymers and the functional group as well. We also, as water purification is one of the integral part of an entire filtration setup. So, apart from that, you also have to take into account for the detection of contaminants. Now, when it comes for the detection of contaminants, we used something known as composite paste sensor. So this one was our first work, which is published in Diamond and Related Material, where we used a functional ionophore to detect lead in water. And apart from that, we used something known as, again, a MOF, which is now an iron ferric pellet MOF, and we used it for selective detection of lead in contaminated stream. We are also working in electrocatalysts, which used for hydrogen generation from wastewater stream. And this is the new area that I had started actually in collaboration with one of my senior colleague over there at Pilani. And we used something again known as the metal organic framework, titanium-based metal organic framework, where we are using different type of doping. So in this case, we used novel, that is iron doping, which is being used for the first time for electrocatalytic hydrogen evolution reaction. These are some of the patents that we had filed when, in the first column, we can, these are all filed, are provisionally filed when I'm in my affiliation with Pilani. And the other column is during my tenure in GE Appliances, Marmon Waters, and my student as a student at IIT Kharagpur. So these are some of the prototypes which have been developed. So this is the one which we developed, or I developed along with my supervisor when I was a student in IIT Kharagpur, and this is actually a fluoride filtration unit. This one is actually the one over here, that is a process of preparing chemically treated carbonized bone meal. This is an Indian patent which got granted very recently. And we used this material in order to make household fluoride filters or community scale fluoride filters, and along with my supervisor, Professor Dev. And we used a composite bed consisting of soil material and this chemically treated carbonized bone meal in order to remove fluoride. These prototypes are being made during my tenure at GE Appliances, where we again used polymer beads for detection of lead ions and surfaces, mainly leak detection surfaces that can be used in refrigerators. This is the one which we developed during my stint, during my current affiliation at Pilani, where we had given this kind of setup to one of our industrial partners who funded this project for a lab-based lead detection prototype that's mainly being used to detect lead. And this structure contains buffer solution which can actually morph, or which can actually stop the hindrance that is caused due to the coexisting ions in lead detection. So it contains 3 tanks. 2 tanks are made up of buffer, which morph the effect, and the one which contains lead solution. And it's connected with a simple Arduino circuit that's being used to say, or that's being used to alert the user whether the solution is consisting of dangerously high levels of lead or it's safe for drinking. These are some of the works that we do in our lab at that is a water and energy sensor lab at Pilani. So we make sensors and specialized surfaces, membranes and adsorbents. We also work on electrospinning. We work on the flow modeling through porous media and biocidal extraction, where we extract very plant-based natural ingredients from resources, and that can be used for medicinal purpose. So this is our lab. Very happy faces. All these are PhD students and masters and BTech students. Very happy faces, and during some of our lunch and dinner exercises to keep them happy and to keep our appetite happy, actually. So these things, before coming on to the facilities, I'd like to introduce to my students who are actually the pillars of all the work that we are doing in our lab at WITS. So he's Dharmesh. He's working on heavy metal detection sensor. He's again just joined after Dharmesh, Mr. Manu. He's working on the electrospun nanofibers for water purification. He's Ankit, working on membrane bioreactor for emerging contaminants removal. He's Anemic, working on thin film nanocomposite membrane that's used for dye desalination, that is dye removal and salt recovery from the dye waste wastewater. We have she was actually my master student who continued with her PhD, and she's working on the electrocatalysis for hydrogen generation. And he's the new addition, is a part-time PhD student working in an industry in Mumbai, in Maharashtra, where he will be working on antifouling membrane reactor, which can be used for analyte concentrations. These are of my master students. Nilargya, he was working on strengthened fiber matrix, and he has completed his masters and now into looking for a PhD positions. She's Priyanka. She worked on sensors. We are communicating the publication that she has worked along with my PhD student Dharmesh to a journal. He is Akhil. He worked on composite membranes, and the MOF cloth work that I presented was actually being mainly done by Akhil and Prapti. And he was Vashisht. He's actually working on food processing. He worked under me, and he had written a very good review paper along with one of my collaborators at IIT BHU. And he's currently placed as a PhD student at IIT Bombay. So all of these placed are in very good positions. Akhil is in Biocon, Priyanka is in Pidilite, and he's doing his PhD from IIT Bombay. So these are some of the facilities that we have, apart from the pillars of the work that being mainly carried out my students at BITS Pilani. So we have the batch ultrafiltration cell, we have the flat sheet membrane caster, the cross-flow ultrafiltration cell, electrochemical cells, hollow fiber cell, shaker, incubator cum shaker. We have the very new addition, which is the most famous toy that we have, the electrospinning unit. And again, a very famous toy is it's the hollow fiber spinning unit. So these are some of our funding partners: Gujarat Fluorochemicals, MKS Vision, based in US, the Science and Engineering Research Board from the Government of India. We have Purita, which is again an industry in Mumbai, based in Mumbai, in Maharashtra, and BITS Pilani. These are some of our collaborators from Anna University, from CMERI, RMIT. We are working with Professor Namita and Professor Nava very closely. We have Professor Janiak from Heinrich Heine University in Düsseldorf. Carolean Institute, we are working with them on the development of this sensors, and University of Rhode Island in US, where we are working with Professor Joseph Goodwill in order to develop adsorbents for heavy metal removal. So the beauty lies around. This is the famous, beautiful campus of Pilani, the famous clock tower that we have. You can see the stunning views over here in the night, in the morning. And the only temple which is devoted to Goddess Saraswati that is present in the Pilani campus. And it's one of the famous temples where the goddess of education resides in the temple, not only in the temple, but in our heart as well. So Pilani is actually heard about BITS Pilani, probably everyone, but we don't know where Pilani actually is. So it's in Rajasthan, and it's in the Jhunjhunu district. So it's around 200 kilometers from Delhi and 250 kilometers from Jaipur. So all of you who are listening to this talk, you are most welcome to visit us at any time of the year, but avoid during May or June because it's too hot during that time. So, but anytime you're free to visit me or drop by me for any discussion or for seeing our lab facilities on the campus. Oh, where did this come from? Okay. Oh, I'm sorry. Thank you. And you have any questions? So I'm happy to run away from you.
Thank you, Somak, for your talk. Thank you very much. And indeed, the campus does look beautiful. It looks like a really nice place.
Thank you very much, Phil.
Now, it's time for questions. So I'm going to just put it out to the audience. If you have any questions, please feel free to either unmute yourself and speak or chuck a question into the chat. Any questions? Anybody want to unmute and ask a question? Somak, I had one question, and you'll have to excuse me because I'm not an expert at all. But from what I understand, moths are not very tolerant to aqueous environments. Some are and some are not. So I'm just wondering if the stability of the moths that you're using in water has played a role in their uptake capacity, or otherwise played a role in the development of these composite materials that you've created.
Yeah, it's a good question. Actually, it's actually one of the drawback that moth usually do have, that it's not very much water stable. This is one of the primary reason why we had to immobilize it in a surface on the surface, that is moth cloth. But yes, some of the moth which are mainly terephthalate based moth, they are somewhat water tolerant in comparison to most of the moth that's been used for let's say any other water based application. MOF previously was used for gaseous application, but now MOFs are used for water application as well, and mainly terephthalate based MOF or zirconia based MOF. These are mainly used for water based application. And stability, yes, it's something that is not so much good, but we can see that the structures or the nodes which are present on the ligand surface, they are the one which gives you an upper edge for the uptake of the major contaminants that is present in water. In our case, aluminium, it has high affinity for fluoride making aluminium fluoride complex, and because of that, it attracts fluoride and sits in the ligand structures along with the exchange with hydroxyl ions. And the reason for the decreasing water stability of MOF, we had to immobilize it so that those immobilized surfaces, those surfaces where the MOF are immobilized, can be used for our end application.
Excellent. Thank you, Somak. We have time for one more question. I'll just put it out to the audience one more time. Please unmute, or you can type your question into the chat. I'll just give you a minute to consider your question. No more questions for Somak?
No plan. Yeah.
So everybody understood everything.
Everyone understood.
Thank you very much.
So before just concluding, I just like to reach out to my audience. I cannot see here, but so I like to reach out to my audience for a quick gesture about how science can be intriguing as well as exciting at the same time. It is not boring actually if you do it in the right way. So everyone knows about something known as the Briggs-Rosher reaction. So Briggs-Rosher reaction is something very famous that is used for the It's a kind of a traffic light based reaction. Why a traffic light? Because you use a dye over here, and the dye in a sugar solution, in an alkaline sugar solution, it starts oxidizing, and it becomes green, and the solution becomes amber color. And this occurs in a reversible mechanism. So when you use this kind of dye in an aqueous alkaline solution, the oxidation is reversible, and the color of the solution, it starts changing from amber to red to green, and then again from green to red to amber. So this is mainly mimicking the traffic light. So we use this kind of mechanism to use in something known as the aesthetic handles of refrigerators. Now, in all cases of products, something very aesthetic nature of the product needs to attract the customer, and this is a new branch of design of products, which is aesthetic design, and it's a vast subject, and it's coming up into the picture now, where designing of appliances or products are very much necessary for customer attraction and satisfaction. So we use this kind of mechanism when I was working with GE appliances, and you can see over here that when we made this, and it's been amber, and now just give it a gentle shake, it starts again red, and then again comes amber. So this is something we utilized in something known as the aesthetic handle. So it can give a customer satisfaction and creates the aesthetic awareness in those people, where you can actually sell the product with a much higher grading and much higher awareness. So this is actually blending science with something in a management, and something in customer appliances, which can give you a good edge over other factors in the market. So thank you very much for, and especially thank to all the listeners, the Professor Namita, Professor Naba, and Philip for organizing this talk. I'll also, as you said in the beginning, I'd like to acknowledge the original inhabitants of this land. Apart from that, the Australian government for allowing me to enter the country, to work over here for a month, and all the people who made my stay very pleasant and beautiful over here in Australia. Thank you very much.
Thank you, Somak, and safe travels.
Thank you.
Thank you very much, Phil.
Pleasure. Thanks, everyone.
Thank you. Thank you very much. Yeah. Right, so we can drop off now.